Let's talk about the basic trigonometric identities. There are 5 sets of trigonometric identities that we have at the heart of trigonometry, and that's not to say that we can't create other identities, and we're going to do that, but these are the 5 basics that we really need to be comfortable working with the entire course. So the first set are the reciprocal identities, and these bring into our trig our reciprocal functions. So sine and cosecant we know are reciprocal functions. We can write sine as 1 over cosecant, or conversely, cosecant is equal to 1 over sine. Cosine secant, reciprocal function, so cosine is equal to 1 over secant, or secant is equal to 1 over cosine. Tangent, 1 over cotangent, and cotangent is 1 over tangent. These are all true just through the basic definition of a reciprocal identity. The next set of identities are the quotient identities. Tangent theta is equal to sine over cosine, and cotangent theta is equal to cosine over sine. I'm going to show how these work in just a few minutes. So I'm going to go through and show how each of our sets of identities works. But I just want to run through what the basic identities are first. Then we have our Pythagorean identities. Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. Now, honestly, this is the only one of those I actually remember. The sine squared plus cosine squared equals 1. With time, you're going to recognize these. I say this is the only one I know, but really I recognize all of them. But if there's going to be one to memorize, it is a sine squared plus cosine squared equals 1. I'm going to show you how to get to these other two very easily. We know that there is a Pythagorean identity for every trig function, and we'll see how to get those in just a little bit. Then we have our even and odd identities. These are related to the even-odd properties of functions. So sine is an odd function. Sine of negative theta is equal to negative sine theta. Cosine is even. Cosine of negative theta is equals cosine theta. And tangent is also odd. Tangent of negative theta is equal to negative tangent theta. All of their reciprocals match up there. And then finally we have the cofunction identities. Sine theta is equal to cosine pi over 2 minus theta. Cosine and sine both cofunction identities, so we can go both directions. Cosecant, secant are cofunction identities, so we can apply it the same way we did for sine and cosine. And then tangent, cotangent, also a pair of cofunctions, so we can convert between those two. So keep in mind, reciprocal versus cofunction, the only reciprocal pairing that matches up with the cofunctions are the tangent and cotangent. They're both reciprocals and cofunctions. Sine, cosecant are reciprocals, however sine and cosine are the cofunctions. So again, what do all of these things do for us? All these identities, the purpose of these things is to allow us to convert from one trig function to another fairly easily and without changing the structure of the equation at all. So we've seen how we can evaluate these trig functions, but at times when we do that, if we plug things in the calculator, that gives us an approximated value. These allow us to translate between different trig functions without changing their value one bit. They are exact equalities. The Pythagoreans actually allow us to relate it to an external number of 1. So the Pythagoreans are the only set of identities that allow us to take a pair of trig functions and relate it to a concrete number, that one number being 1. Of course, we could I guess do the same thing with reciprocals. We know anytime we multiply a reciprocal by itself, it gives us 1. So let's talk through how these identities work. And I'm going to start with the quotient identities. Let me first define the sine, cosine, and tangent functions. So if I write out the sine function, we know that sine is equal to the opposite over the hypotenuse. The cosine, theta, is equal to the adjacent over the hypotenuse. And the tangent is equal to the opposite over the adjacent. Now, actually, in terms of sides there, we got all the sides related in some way after just those first two identities. Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse. Tangent relates two of those sides in a different way. It takes the opposite and adjacent that we saw before and relates them in a slightly new way. So that means the tangent function is really nothing new. It's not doing anything new for us beyond the ordering or beyond the structure. It's not relating any new sides, it's just relating the sides in a different way. So what that tells us is we should be able to relate the tangent through sine and cosine, and we can. If we think about how we could end up with the opposite over adjacent, we need the opposite on top, we need the adjacent on the bottom. That would mean I probably need to divide these two things. And if we were to divide the sine by the cosine, we would multiply by the reciprocal, and that would mean the hypotenuses would cancel. And that is why we can say that the tangent of theta, or of an angle, is equal to the sine over the cosine. The exact same thing would be true for cotangent, except for then we would want the adjacent on top and the opposite on the bottom, so we would have the cosine over the sine, and that's where we get those quotient identities from. Let's move on to the Pythagorean identities. We'll look at those next. If we think about the Pythagorean theorem tells us a squared plus b squared equals c squared. That's not really what the Pythagorean theorem tells us. That's the little shortcut we have for it. But what the Pythagorean theorem says is if we have three sides, I'm going to go ahead and name these sides a little bit differently. We'll call it the opposite, the adjacent, and the hypotenuse. Well, I can relate those three sides by saying the first side, or the first leg squared, plus the second leg squared equals the hypotenuse squared. Now, we tend to name the opposite A, or the adjacent A, and then the opposite B. The two sides we name A and B, and then the hypotenuse is always C, but that A squared plus B squared equals C squared is really saying the square of the two legs of a triangle added together equals the hypotenuse squared. That is its more formal, that is the formal Pythagorean theorem. So let's say I want to take this and just rearrange the pieces a little bit. Let's just, for the fun of it, divide everything by the hypotenuse. And because I really want to get a 1 over here, so I'm not going to divide just by the hypotenuse, I'm going to divide by the hypotenuse squared. We know we're allowed to divide by anything as long as we do it to all sides of an equation, as long as it's not 0. And obviously if we have a triangle, the hypotenuse is not equal to 0. So I'm just rearranging some pieces, and so I get the opposite over the hypotenuse squared plus the adjacent over the hypotenuse squared equals 1. Well, what is the opposite over the hypotenuse? That is the sine function. So we'll have sine squared. What is adjacent over the hypotenuse? That is the cosine function squared. And 1 is obviously just 1, and that is the first Pythagorean identity. So the Pythagorean identities are just taking into consideration the sides slightly rearranged in order to get the ratios of sides, because we know that trig functions are just ratios of sides. So we're trying to get to a ratio of sides, and one way we could do that is divide by the hypotenuse. Now, why didn't I divide by, say, the opposite? Well, I could have. If I divide by the opposite, I would have ended up with 1. Adjacent over opposite is the cotangent, and then the hypotenuse over the opposite would be the reciprocal function for the sine, or the cosecant. And then we could apply some other identities there. We could get to those other two Pythagorean identities by dividing by all the sides, but I'm going to do it I'm going to do it a little bit more efficiently. Now that I know that this statement is true, get rid of that errant line. Now that we know that this statement is true, sine squared plus cosine squared equals 1, I told you that's really the only one you need to know, to memorize, because I can get from this one to all of the others. So let's say I were to take this, and I'm going to divide all the pieces by sine squared. This would essentially be dividing off a different side from that original calculation. Well, if we have sine squared divided by sine squared, that's going to give us a 1. Cosine over sine squared is a cotangent squared. And then 1 over sine squared is that cosecant squared. And that gives us another one of our Pythagorean identities, the one with the cotangent, that bottom one there. And then let's say I want to take this same Pythagorean identity, so let me just rewrite it. And this time I'm going to divide by the cosine. I'm going to divide by the cosine squared, of course, to get a 1 there. Sine over cosine is tangent squared, because it was squared before. We have our 1 there now, and then 1 over cosine squared is secant squared. And so notice that is the third of our Pythagorean identities, written in a slightly different order. But we know with math we can always reorder these things. So if we want to write sine squared as 1 minus cosine squared, we could do that. or cosine squared equals 1 minus sine squared. That is also true. So we can always rearrange these however we need to use them. So the question is then, how do I know what to do? If I want to start with the sine squared plus cosine squared equals 1 and I want to get to one of the other ones, how do I know what I need to do? Do I divide by sine or cosine? Well, think about what you're trying to get to. If you see a tangent squared in your equation, I know that tangent is sine over cosine. So I'm going to need to divide everything by cosine. If I see that I have a cosecant in my equation, I know that cosecant is 1 over sine, so I'm going to divide everything by sine. So think about what squared function you have. If you have a squared function in your equation, there's a good chance you can use a Pythagorean identity to help you in some way. Let's next move on to the even and odd identities. These ones are maybe the most abstract at this point, but let's talk about them. So if we think about the signs of the different trig functions, we know that all signs are positive in the first quadrant, or all trig functions are positive in the first quadrant. Second quadrant, only the sine function is positive, along with its reciprocal of cosecant. In the third quadrant, tangent and cotangent. And then in the fourth, cosine and the secant. So remember, these are kind of the the three initial trig functions, and then their reciprocals always match up. So what does it mean for a function to be even? Remember, a function is even per the definition, if when we take the variable, we'll call it x or theta. Let me switch it over to theta since I've been calling the other things thetas. If I make that theta negative, that gets me back to the original function. That is an even function. If when I replace that variable, I get the negative function, well, that function then is odd. So even if when we replace the variable, it becomes a positive function, and then it's odd if when we replace that variable, we get the negative function. So let's think about what happens when we replace sine with a negative angle. So if I replace that angle with a negative, well, there's four possibilities for that angle. It's taking us into the first quadrant, second quadrant, third quadrant, or fourth quadrant. So let's, for right now, say that we have an angle in the first quadrant. If we were to replace that angle with a negative angle, well, we travel by the same amount, but downwards now, and that would take us into the fourth quadrant. Or conversely, if we'd instead started with an angle in the fourth quadrant, traveling the negative angle would have made us move backwards into the first quadrant. So the first and the fourth quadrant will always match up. So if I take sine of that negative angle, meaning we're now looking at the fourth quadrant, well, we're going to have the exact opposite sign as before, because sine I should say, in the first quadrant is positive, but in the fourth quadrant it's negative. So by taking sine of the negative angle, we get the negative of what we had at the start. We know how these reciprocals work, the reference angles work. The reference angle is the same amount. We're counting off that x-axis by the same amount. The only difference is we're ending up in a different quadrant. So sine of negative theta is equal to a negative sine of theta. If we compare that to cosine of negative theta, moving down here, again, I know that if I were to move up here, it's the same amount off of the x-axis. The reference angle is the same. I'm in a different quadrant though. So now when I take the cosine of negative theta, because I'm in the fourth quadrant, cosine is positive, well, it's positive in the first as well. So it's equal to the positive cosine of theta. And then finally, if I look at tangent, well, tangent of negative theta moves us between the two same quadrants we've been looking at, the first and the fourth. Tangent negative theta, well, in the fourth, tangent is negative, but in the first, it's positive. So that means that, just like with sine, we get the negative tan theta. Now, I said this was true in the first and the fourth, but what if we had instead looked at the second and the third? Well, they're going to match up as well, because if we have a theta that takes us into the second quadrant, well, the negative theta would travel the same amount around, taking us into the third quadrant. And so what that means is that we're always going to be looking at one of these two pairings. If we start by going into the second quadrant, negative theta would put us into the third. If we started by going to the third, negative theta would take us into the second. And sine in the second is positive, in the third it's negative, so this is still true. Sine in the cosine rather, in the second is negative, in the third it's still negative, so this is still true. And then tangent in the second is negative, in the third it is positive, and so this is still true. They're still off by that sign. And so that is why sine is an odd function, tangent is an odd function, and cosine is an even function. And that brings us to our last set of identities, the reciprocal identities. So for the reciprocal identities, I'm going to draw out a triangle. And so this triangle, I have my angle theta here, and I know that this would be the opposite side. I know this would be the adjacent, and of course the hypotenuse is always going to be the hypotenuse. So if I define the sine function, sine is, I know, opposite over the hypotenuse. But let's, for the fun of it, say I switch to this angle right here, the angle in green. Well, it's part of the same triangle, so it's going to somehow relate these sides in a slightly different way. So if I were to say sine now, sine of theta, well, that would be equal to the adjacent over the hypotenuse. And the adjacent over the hypotenuse, usually when we say adjacent over the hypotenuse, we were thinking of cosine. And that's not wrong, it's just we changed the angle of perspective. So if I don't relabel the sides, the opposite side here is what I originally called the adjacent. So what that tells me is that this sine of the new angle is really equal to the cosine of the old angle. I could do the exact same trick for the sine, where this would be equal to cosine of my new angle in green. So this is why we have these cofunction identities, because if I think about what pi over 2 minus theta is, it is just the opposite corner of a right triangle. I know the angles of a right triangle add up to 180 degrees, or pi degrees. Pi over 2 or 90 degrees is guaranteed to be one of the angles, leaving pi over 2 or 90 degrees for the other two angles. So by moving between those two angles, looking at the complementary angle, I'm just switching what I'm calling the opposite and what I'm calling the adjacent. All right, so now that we understand what these things are doing, why are they useful? So let's say we were to start with the function sine of pi over 5. Well, there might be times, and there will be times in this class, when we don't want to work with sine. Instead, we'd rather work with the function cosine. And so using what we just talked about, we know that we can rewrite this as cosine of pi over 2 minus pi over 5. Now to do this calculation, we're going to need a common denominator, which will be pi over 10. And so we'll have 5 pi over 10 minus 2 pi over 10. And that gives us cosine of 3 pi over 10. So we've been able to take sine and write it in terms of cosine. And we could do the same thing going the other direction. We could do the same thing with secant and cosecant. But we can always vary between the sine and the cosine, tangent, cotangent, secant, cosecant. Maybe we have known values for the sine and cosine. Maybe I know that sine theta is equal to 2. I know that cosine theta is equal to 5. Now if I wanted to, I could draw this triangle out and I could say, well, theta, well, that sine is going to be the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. Notice its hypotenuse is matched up. But if I thought about it, I could have found tangent very easily by simply saying it's sine over cosine. And I wouldn't have had to draw anything out. I wouldn't have had to do any math there. I would have just had it right away. So again, allowing me to relate my trig functions in a very efficient way. Then there might be times that we see that we have something like sine squared of pi over 9 plus cosine squared pi over 9. And we might be asked to find the exact value of this. Well, I have no idea what the exact value of pi over 9 is because that's nowhere in my unit circle or my special triangles. However, with my Pythagorean identity, I do know that as long as I have the same angle within the sine squared and the cosine squared function, that is always equal to a 1. So my answer would just be 1. Now again, there's lots of variations on these. We could see cotangent and secants and tangents instead. We could see negative ones instead of positive ones. So for instance, if we think about, let me scroll all the way back up to our Pythagorean identities, maybe instead of seeing the sines and the cosines or even seeing it in this exact pairing, maybe we see a Tangent squared of 29 degrees minus secant squared of 29 degrees. And I want to know the exact value for it. Well, 29 degrees is very close to 30, which is in the unit circle, but it's not. So I can't say it's 30. I can't just approximate it. I want to find the exact value. And this isn't exactly what I see here, but I see it has all the same pieces. I have that tangent, I have the secant. So if we think about how we could take this thing and rearrange it, what if I were to have subtracted the secant over to this side? Well, then I'd have 1 plus tangent squared of theta minus secant squared of theta equals now 0 over there. But then if I want to figure out what tangent squared minus secant squared equals, I take the 1 back over. I would do that by subtracting, and so that means that tangent squared minus secant squared must equal -1. And so now I have my answer, it's -1. And so we can play around with these identities, we can massage them where necessary and get to the answer that we need or the format that we might need. In fact, it might not even be that we have that sine and the cosine there directly. It might be that we see something like sine cosine. But what we talked about in the first example is we can always take sine converted over to cosine. So if I see sine times cosine, there's a good chance that I might be able to write that as a sine squared. Now the angles have to work out perfectly. It has to work in the cofunction identity, but there is that chance. And so these are just all things that we want to have memorized. We want to know all of these identities off the top of our head because we don't know where they're going to come up. At any time, we might have to rely on knowing one of these to convert to a trig function that we need to use, to simplify an angle, to simplify an expression. And so the majority of these are allowing us to convert between trig functions with really little expense. The even odds and cofunctions do make us change the angle, but that's not always a bad thing. Sometimes we want to change those angles to simplify a negative sign. So we want to know these identities inside and out.